that I think is really cool. So here we go. Let's start by considering convex functions. Convex function phi, right, in C1. All right, and to this convex function, we're going to associate a bunch of open convex sets like this. So if you give me a point in Rn, right, and a number t positive, right, we're going to define the section. This is the section of phi, the convex function, centered at x0 and with height t as this set. So the set of all these x's here such that phi of x is strictly smaller than this quantity. And here we see that this part is just the tangent plane of the phi at the point x0, phi of x0, and we have just lifted this tangent plane by t. Remember, t is positive, all right? So, and then we're looking at all the x's, right, such that phi of x is smaller. It's underneath. I have a picture, I'll show you. So remember that, so tx naught of x is this part, right? It's just the tangent plane at this point. So here's the picture for the section. So this is the graph of the phi, right? This is the x0 arbitrary point in Rn, right? And then you look at the tangent plane, tx0, all right? It's a tangent plane, and then you lift that plane by t units, so it's not tangent anymore. Now it's a secant plane, like this, right? I'm gonna chop the graph like this, and then this part we project down to Rn. So this part, so this open convex bounded set is what we call a Monge-Ampere section of the phi, of the function phi. Notice that although we call x0 the center of the section, it doesn't have to be necessarily the center of mass of the section. We just say the center, we call it the center, but it doesn't have to be the center of mass of the set. All right. Next, we're going to introduce a measure that's associated to this convex function phi. All right, that's very easy because this is what we do. Take a Borel set E. All right, you pass it through the gradient. So the gradient of phi now goes from Rn into Rn. So you pass the set E through the gradient, and then take just Lebesgue measure of that. So these two bars mean just Lebesgue measure, all right? So when we call that mu phi, so that's the Monge-Ampere measure associated to this phi. So here's a little note. If phi is in this Sobolev space W2n log of Rn, then it turns out that the phi is C1 is continuously differentiable, and the Monge-Ampere measure of a Borel set E amounts to just integrating over that set E, right, the determinant of the Hessian of phi here. All right. I proved that a couple of years ago. This is easy to see when you have a function that is C2. It's twice continuously differentiable. So that's easy to see, but then I prove that that's true when you can go down to a Sobolev space like this. So what we have to bear in mind is that the Monge-Ampere measure is just a weight. It's a measure that has a weight, a density, and the density is this. Notice that the function being convex makes this a non-negative function, the determinant of the Hessian, all right? Very good. So given the phi, we have a bunch of open convex sets, the sections, and then we have a measure. So we have a third object related to the phi like this. Now let's fix the phi strictly convex, right, in the Sobolev space from earlier. And let's add the assumption that the determinant of the Hessian, that's strictly positive for almost every x. So this is, we know that this is going to be bigger than or equal to 0 because of convexity. But the condition is that it's positive, strictly positive, almost everywhere. All right. All right. And now, given the domain omega, all right, we're going to think of a mapping, measurable mapping that to each x in omega, all right, associates an n by n symmetric matrix. So A of x is an n by n symmetric matrix. And how does this matrix relate to the phi? Well, like this. There are some numbers, little lambda, big lambda, such that in the sense of non-negative definite matrices, we have these two inequalities, this one and that one. What this means is that if you give me an x in the omega, all right, now the matrix A of x is going to be controlled by the Hessian inverse of the phi. In this sense, this means that the eigenvalues of A of x are controlled by the eigenvalues of the Hessian inverse. Remember that this is the inverse exists because for almost every x because of the positive determinant here, right? All right. So in this way, the A is shaped by the Hessian inverse of the function phi. All right. If we're going to think that the lambdas are just one, we're saying that the A is just the Hessian inverse, right? But we allow for some room. Now, once you give me a matrix A or a mapping A like this, we think of an elliptic operator. So that's going to be the trace of A times the Hessian of U. So the operator is L sub A, and it acts on a matrix on a function U like this. So it's a trace of the matrix A times the Hessian of the U, right? If you think that the A is just the identity matrix, so this is just a trace of the Hessian of U, that's just the Laplacian, all right? So if A is just the identity matrix, this all falls back to the Laplacian. So what we're thinking is just these deformations of the Laplacian. Very good. Where is this all coming from? This is coming from the theory for the Monge-Ampere equation. Now, the Monge-Ampere operator is this. It acts on a function phi as the determinant of the Hessian of phi. So if the Laplacian is the sum of the eigenvalues of the Hessian, right? The Monge-Ampere operator is the product of the eigenvalues of the Hessian, right? Now, this is clearly highly nonlinear function in operator in terms of the phi, right? It's not additive, for instance. So if we linearize this, so if you fix a phi, right, and look at the linearized version of this operator at U, that means this is what we call the Frechet derivative or the Gateau derivative. You take the limit, it's like a directional derivative, right, at phi in the direction of U, like this. It turns out that this operator, this limit, in the end, is just the trace, right, of Hessian inverse times Hessian of U, right? Times a function here, times the determinant, right? So you see, this is pretty much the same as this. When A is not just equivalent to the Hessian inverse, it is the Hessian inverse. So that's where this is all coming from the theory of Monge-Ampere. That's why there's going to be Monge-Ampere everywhere. All right, it's going to be helpful to keep in mind the following reference. And this is the basic example for all this. What happens, so we've been talking about a generic function phi, right? Let's pick one, like the simplest one we can think of. Let's just pick the usual paraboloid, 1/2 x squared, right? X is in Rn. Then the second derivative of that function is clearly the identity matrix, right? Therefore, it's so the determinant is 1 of the Hessian, right? Therefore, the Monge-Ampere measure associated to this paraboloid is just Lebesgue measure. And a brief computation shows you that the Monge-Ampere sections, the sets, when you chop off this paraboloid, what you get is balls. So the sections of this paraboloid are just the Euclidean balls with certain scaling, right? With square root, because there is that square over there. All right. And then what does it mean that A is comparable to the Hessian inverse of this phi2? Well, since the Hessian inverse of phi2 is just the identity, right? It means that A is just like the comparable to the identity matrix. What does that mean? Well, we call that A uniformly elliptic, right? And what it means is that there are these two numbers, lambda positive and big lambda finite, such that all the eigenvalues of A of X are in this interval, right? Where the left endpoint is away from 0, right, and the right endpoint is away from infinity. So there is this finite box, lambda lambda, where that hosts all the eigenvalues of this matrix, or the n eigenvalues of this matrix, for almost every x in the omega. So the box doesn't change, doesn't depend on the x. So all the eigenvalues dance in that little interval as you move the x. Right? And now, in this scenario, when you have all these elements, there is this groundbreaking result that says that, all right, if you have a function that is non-negative, all right, and it is a solution to your operator, right? Trace A, Hessian U equal to 0 in omega, where the A is uniformly elliptic, then the function U has the Harnack property, meaning that the supremum of U is controlled by the infimum, where this constant is a structural constant that depends only on the lambdas, the size of the boxes, right, and dimension. And it happens uniformly for any ball, right, for any Euclidean ball in the omega, all right? So the question is now the following. Now you can see it coming. Okay, for this specific particular convex function, we have a nice measure, we have a nice collection of sections, just Euclidean balls, and there is this fundamental theorem that gives us a nice control on the solutions for the homogeneous problem. So this Harnack property in particular is going to imply that the U is is C alpha. It's continuous, but it's Hölder continuous for some alpha, right? Alpha Hölder continuous for some alpha. So it's going to be better than what we started with. Right? Right. So the question is, all right, what other functions can I put in there? What other convex functions can I put in there so that we can get a similar Harnack inequality? Right? Of course, the geometry for that new Harnack inequality we're looking for is not just it's not going to be the Euclidean balls anymore. It's going to be the geometry of the sections. So that's the question. What conditions on the strictly function phi guarantee that there's going to be a Harnack inequality, right, for solutions, non-negative solutions, when the A is now comparable to the Hessian inverse of the phi? All right, that's the premise, and that's the question. And here is one condition. We say that a Borel measure mu is in the class A infinity phi, right? You fix the phi, right? If this happens, you can recognize this. If you give me any section S, any Monge-Ampère section, remember the phi is fixed, and then any set inside Borel set inside that S, then if the measure of the E is small with respect to the measure of the S, measured with the Lebesgue measure, so if E inside S is small with respect to Lebesgue measure, then it's also small with respect to mu. That is this condition. So we say that mu is in A infinity phi, this measure, if this happens. Right? This is like a uniform, this is what we call absolute continuity at every scale, right? So, and you may recognize this. This is just the counterpart. We have changed the geometry, right? Instead of a ball here, we have a section, right? This is just the famous Koyfman-Pfefferman characterization of Magenhaupt weights, of A infinity Magenhaupt weights. So all we're doing is changing the geometry. Instead of putting Euclidean balls here and there, just use the sections. So here comes a groundbreaking result from the 90s by Caffarelli and Gutierrez that says that, all right, if you have that your phi is C2, that the Hessian is positive everywhere, and that the measure has this nice property, it's a very mild condition, right? Then you give me any matrix A comparable to the Hessian inverse, right? And then you have the Harnack, so every solution, non-negative solution, right, will have the Harnack inequality, right? But you see how the property holds on the natural geometry and the geometry of the sections, right? So this is a groundbreaking result from the 90s, and the hypothesis, this hypothesis of the Hessian of phi being strictly positive everywhere, right? Even if at one point, if it's 0, the proof doesn't work. So this hypothesis, strictly positive, is essential to the proof. All right. So impressive as this theorem is, there is an example. There is an example of a certain PDE, right, that falls short of meeting the hypothesis. All right. Here's the example. These are well-known operators. So what you do is you fix two dimensions, n1 and n2, right? And then you have Rn1 cross Rn2, right? And then you have your x1, right, in Rn1, your x2 in Rn2, right? And then you define this and you fix gamma positive, all right? And then what you do is this. So this G sub gamma is going to be an operator, right, that acts on you as follows. On the first n, sorry, the first n1 dimensions, that's going to be just the Laplacian. So the Laplacian here, right? And then the Laplacian 2 is the Laplacian on the second part of the dimension, so n2, right? But here you're going to put this weight. So you see that when x1, and when you get close to x1 equals 0, this command starts being degenerate, you say. It collapses. When x1 is 0, this part, we don't see it, right? The operator, that's not there. So this is a well-known operator. It's a degenerate operator, an elliptic operator. And I will try to make the argument now that this could be dealt with by the Caffarelli-Gutierrez theorem, but there is one small obstacle. And all right, so we have that. Let's see. So I want to write this, right, as something like that. How so? Well, do the following. So you have your equation, say, equal to 0. So you have this, right, equal to 0. Then divide by x1 to the gamma. So you have this. So all I did was I divided this, right? Yes. But then we realized that this expression, right, is the trace of some matrix A sub gamma, right, where the A sub gamma is this. All right. In the first n1 cross n1 box, we have 1 over x1 to the gamma, and then on the second n2 by n2 part, right, it's just the identity matrix. All right. That's it's not hard to see, right, that this whole thing, right, you can write as this trace, with this matrix. All right. And now we'll see that this matrix that we write like this, remember we have this equal to 0, right? This equals 0. Right? So this is equal to 0. And now let's see that if we define this function, this convex function, right? It's a simple computation to show that this A gamma is comparable to the Hessian inverse of this convex function. And the comparability constants here will depend only on dimension and the gamma. So it's a structural constant. Right? So we have everything, right? Pretty much everything from the statement here. But look, what is the catch? Well, if you look at the determinant of this thing, so here you can do a determinant of this because they're comparable anyway. So here, here, no, the determinant of this is the inverse of P. You get, so think of just dimension one, right? If you take two derivatives, you get x1. So this comes x1 to the gamma, x1 to the gamma. And that equals 0 on the hyperplane x1 equals 0. So the determinant of this thing vanishes, right, on a whole hyperplane. And that keeps us from using the Caffarelli-Gutierrez theorem, because you see here, the assumption, the crucial assumption is that the determinant of the Hessian be positive everywhere. So, so close to fitting this sub-elliptic operator that has a whole machinery behind it. In order to study this, we have the Carnot-Carathéodory metric, a bunch of other tools that are not coming from Monge-Ampere. So being able to deal with this by means of the Monge-Ampere tools, that would be nice. But since the determinant is 0, we cannot use the Caffarelli-Gutierrez theorem. So what to do? Let's introduce a new condition that's going to allow for the determinant of the Hessian being positive almost everywhere. You see? And this is in a hyperplane. It's going to have measure 0. So, so now determinant positive almost everywhere. It's a big jump. Now I'm going to introduce a new condition, right? Now some notation. If you give me 2 points x, x0 in Rn, I'm going to define this delta function, delta phi, at x0 x as phi minus its tangent plane at x0, which is this part here. In particular, if you recall the definition of the sections, right? The section now can be rewritten as the collection of those points such that this quantity is smaller than t. So you see, by doing this simple thing, we can start thinking of this delta as a kind of a distance. And so we're saying that these sections are actually balls with respect to this distance. It's not going to be a distance, but it's going to be close enough. All right, so that's a delta. Now let's introduce the d. The d is this long thing. It's a Hessian inverse times grad phi at x, grad phi at x0. So these Japanese brackets, these are just the dot product, right? The inner product in other. So that. If you fall back to the typical paraboloid, this is going to be just this. It's going to be the distance from x to x0 squared, and this is going to be the distance. Maybe this one is going to be 1/2 of the distance. This is going to be 1/2 of the distance squared, the Euclidean distance, and this is going to be just x minus x0 squared, for the usual reference of the paraboloid. All right. In general, we have these quantities. Now, the condition is this. We will say that delta is controlled by d, all right, if there exists some c positive such that, well, delta is controlled by d. See them? And this happens for every x0 and for almost every x. The difference here we use for almost every x, because you see we're using here Hessian inverse, and that exists for almost every x, because that was the assumption here. Not every x, just almost every x. All right. The claim is that this is the property we want now. And this property is going to allow us to get a Harnack inequality. Here it is. This is something I proved a few years ago. So essentially, this is the assumption. If delta is controlled by d, then you can have a fall PDE, right? With lower order terms, you see you have a first term there, and then a 0th order term, and then a general source, right? It doesn't have to be 0, and such that you have this Harnack inequality. And you see now you have the supremum, and it's controlled by the infimum, and there is another quantity here coming from the source F. All right. So the point is that this new condition, right, is flexible enough to allow for determinant positive almost everywhere, right? And it gives you Harnack inequality. Right? Now, where is this coming from? That's what I wanted to talk about. Where is this coming from? This delta controlled by D. Why is that we arrive at this condition? And we will see later that the Grushin operator from before, to which we cannot apply the Caffarelli-Gutierrez theorem, and we will be able to apply this one. Right? Okay, where is this coming from? That's the point of my talk. This is what I want to advertise, and this condition. Well, let's go back to the usual Euclidean case of the Monge-Ampere, of the Lebesgue measure, the Euclidean balls, and the paraboloid, the uniformly elliptic operator. So how is it that we get a Harnack inequality? Well, when you study Harnack inequality, you realize that there are two properties that guarantee your Harnack inequality. Yeah? The first one is called the critical density property, that says that, and there are some constants m big, million, right, and epsilon small, such that if you take any ball, right, and you look at the place, the probability that the u is going to be bigger than 1,000,000, right? If that's bigger than the epsilon, think that the epsilon is 0.01, right? So it's 1%. Yeah? So if you, and then you have the implication, right? So this reads like this: if u is bigger than 1,000,000, 1% of the time in a ball, then in the ball of radius 2r, then in half the ball, radius r, the u is bigger than 1. That's what we call a critical density property. I'll show you a picture in a second. And then the other condition is called the double ball property, that says that if the u is bigger than 1 in BR, then it's bigger than some gamma in twice the ball, right? So that the function cannot drop to 0 so suddenly. Yeah? So if you go from BR to B2R, and you were above 1, then you remain above some gamma. Right? So these are the two properties that completely characterize the Harnack inequality. All right. And so here's the picture. So this is a picture for a critical density property. So we're saying that, so in this dark part, this is where u is bigger than m, 1,000,000, right? This is very hot, and this is where so here is u is, if this is a circular metal plate and u is temperature, right? So these places are where where the plate is very, very, very hot. Temperature is it's bigger than 1,000,000 degrees, right? So if this happens 1% of the time, then in the middle, right, the temperature is bigger than 1. So if it's very, 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 very hot, often, then in the middle it has to be warm, right? And then the other property says that if it's warm in there bigger than 1, then in twice the ball it's bigger than gamma. It has to be mild. So that's ellipticity. This is what ellipticity does. This is the phenomenon that we call ellipticity. Very good. Now, let's restate this critical density property, but now in terms of the new geometry, the new measure. Right? So you see, now we have sections there. Monge-Ampere sections. There's a fixed function phi. I look at the section, and then the Monge-Ampere measure, right? Instead of the Euclidean geometry, I have the Monge-Ampere sections. Instead of the Lebesgue measure, I have the Monge-Ampere measure. Right? So, and then this is what I want. I would like to have this happen, and for every sub-solution, for a non-negative super solution like this, right? I want this to happen. And as it turns out, this happens, right? And one can prove that this happens, this critical density property happens when the delta phi that we define this distance, right, is a quasi-distance, meaning that it's quasi-symmetric, right? And it has a k quasi-triangle inequality. All right, so that's a quasi-distance, and this is the natural assumption. That's always a standing assumption. That's the bare minimum of assumption that we may have on this delta, so you can have a quasi-metric space and start doing some analysis, right? So we can think that this critical density thing is for free, essentially. Right? It comes with the space. Now the other one, the double Borel property, that's the one. That's the one that's hard. And that's the one, if you go back to the Caffarelli-Gutierrez theorem, right? That is where the assumption on the Hessian positive all the time is used. All right. So how is it that we deal with this double Borel property? Well, let's go back to the case of the Laplacian again for the case of the paraboloid, this uniformly elliptic operator. This is what you do. Suppose you have a sub-solution, a super solution like this, U, right? And you know that U is bigger than 1, say in a ball center of the origin, radius r. So what you want to see is that in twice that ball is bigger than some gamma. All right. And what you do is in the typical proof, if you remember some course, basic course on regularity of elliptic PDEs in non-divergence form like this, what you do is what we say we construct a barrier, something like this. So look at this function for a p to be chosen, to be fixed later. Now, what happens to this function v? Well, look, on what happens on the boundary of the ball BR. Well, then this is r over r. This is just 1. So here on the boundary, right? Here v is 1 minus 4 to the negative p. P is to be chosen, okay? Okay, which is smaller than 1, right? Which is smaller than the u, because by assumption, the infimum of u is bigger than 1. So we know that on the boundary of this ball BR, u is underneath, I'm sorry, the v is underneath the u. And then what happens on the ball BR, 4r? Well, this, if I put 4r here, right, this is 0, right? And the u is non-negative. So the v is underneath the u on the boundary of this annulus here. All right. And then what we do is, all right, if we have say we have that the L, that this L, right, on acting on the V, on the barrier, is non-negative on that annulus, right? Then what you do is use the maximum principle that says that you look at V minus U. V minus U is negative on the boundary of the annulus, and then L at V minus U is this is negative, non-positive, and then it's non-negative. The L inside the annulus. Then the maximum principle says that then the V remains underneath the U everywhere in the annulus. In particular, if you have, so that's what we call it the barrier, right? So this is saying that if the U is above 1 here, it's above this side, and then it's always above the V, right? That's cannot go down, cannot get past the V, hence the barrier, right? So if I look at B2R, so half of this one, right? the u will remain away from 0, because the v is 0 here at the boundary for 2r. All right. So, and that's how then you get that your function u is bigger than this lambda in twice the ball, because the v here is a barrier. Now, of course, you want to transplant this idea in the case of the Monge-Ampere structure, right? So instead of this, right, you think of the distance. Here you have the distance to 0, right? Now use pick any generic x naught, right? Not just 0, and look at the distance to the negative p, right? And that's where this condition is coming from, right? Delta controlled by d, that condition that we saw at the beginning, right? Rather weird. It's coming from this. L acting on this barrier, right? It's gonna be non-negative if and only if this condition happens. So when we ask for the condition, we have everything. We have the barrier, and then we have the double ball property, and then the critical density property was for free, essentially. So we have everything. We can put things together and just run the machine, and you get the answer. Now, examples. Yeah, so we know that this condition is useful, but how many? Is it too good to be true? Well, there's a rich family of functions and they have this property, right? So here, let's look at this one. If you do 1 over p x to the p, where the power p now is between 2 and infinity. So we know that when p is 2, everything is wonderful. It's just the usual paraboloid, right? But then when p is bigger than 2, things still work. So if p is a strictly convex polynomial, it works. If it's a polynomial to some power a, and then there is this property. Suppose that dimension 1, in dimension 1, and then you have a convex function, right? And then the second derivative is going to be non-negative, just calc 2, right? calc 1. Second derivative is non-negative, and then it's like wait. And then if this happens, suppose you take an arbitrary interval AB, all right? And suppose that the supremum of the second derivative is controlled by the average. So clearly the average is controlled by the supremum. But if you have the reverse inequality, we call that RH, reverse Helder inequality infinity. Then the property is true. So more properties. If you have two functions, suppose you have functions phi1 and phi2 that have the property, this delta smaller than d, right? Then the sum also has the property. So this property is stable under just adding functions. Right? And then how do we relate the sections of the sum to the sections? There is a question. Let me see. I missed that. I cannot see the question. Or maybe by the end.
So the question reads, any special results for radial functions or with other symmetries?
Oh yes. Let me get to that. That's a great question. I'm trying to lead there. Let me see. Excellent. So we know that if I add two functions with a property, I get I keep the property, and this is how the sections of phi relate to the sections of phi1 and phi2, like this. So they're kind of equivalent. You the intersection, and now, okay. More importantly, if I have two functions, okay, here, fixed n1, n2, and 3 dimensions, all right? And on each dimension, on each space Rn1, Rn2, you have one of these functions that have the property, and then you add them, but in the tensorial way. You do this. Phi of x is the tensor sum. This is not going to be radial anymore. Of the ones that have the property, then the phi will have the property. So this property is stable under tensorial sums as well, and the sections are related according to this these two inclusions. So to address your question now, look, we said that if I have a power here when the power is bigger than 2, I have the property, right? And this is bigger than 2 because the gamma is positive, right? And this is 2. So this has the property. This has the property, obviously. Then the tensor sum right here, this is the x, right? Has the property, right? And then the conclusion is that so this is the phi from the Grushin operator, right? And then we do have the property for this tensor. And the moral of the story is that now this Monge-Ampere business can be thought of as an alternative to in the study of this sub-elliptic operator. This is already a well-established machinery, right? The Carnot-Theodoric distance and all that. But here's an alternative, very geometric in flavor, that allows you to get regularity for those solutions to those sub-elliptic PDEs. This is not radial, and in the examples, so you can add, you can do tensor sum. Let me see, I have only 5 minutes. Let me just go. All right, so we already said that when dimension is 1, all right, this condition, delta controlled by D, is equivalent to the second derivative, the Hessian, right? Having this reversed Helder inequality. It's a typical example of a Mackenhaupt way, nice Mackenhaupt way, right? And that the supremum is controlled by the average. Right? Actually, in dimension 1, it's an if and only if. All right. So one has the property if and only if the Hessian has this reverse Helder property, right? But when n is bigger than 1, we have an implication. And when n is bigger than 1 now, right, the condition, implies that this weight, determinant of the Hessian, right, will be in this class, reverse Helder class, right? Meaning that the supremum of the determinant of the Hessian is going to be controlled by the average of that determinant of the Hessian. But following the right geometry, notice how here we're looking at the Monge-Ampere sections. So it's a Mackenhaupt condition, but in the right geometry, in the geometry of the Monge-Ampere quasi-distance. And now, however, the converse is not true. There are functions that have this reverse, whose determinant have this reverse Helder condition, but they won't have the property. So in dimension 1, they're the same. But it's always insightful, because remember that convexity is a one-dimensional condition, meaning that if you have a convex function and you restrict it to a line, right, that restriction will be a convex function as a function of one variable, right, the line. And if and only if, right, if a function whose every restriction is convex, then the function will be convex. So that's why convexity is a one-dimensional property. So in this business, the case n equals 1 always gives you some insight as to what should go on. So along those lines, look at this. So this I proved recently, and because I focused on this condition delta controlled by D, and here is what I was saying. So you give me a function phi, let's say C2, to avoid technicalities. Strictly convex functions phi. And then I'm going to restrict that function, right, to an arbitrary line. So I fix an x naught, a point in Rn, and I fix a direction v, right? And then t is going to be my variable, right? So, and then the restriction of p to this line, the parameter is t now, I'm going to call h. Clearly, the h depends on the x naught and the v. All right, so I have now the h is one-dimensional. It goes from Rn to Rn. It's a strictly convex function, right? So then the phi has the property if and only if the restrictions, the second derivatives of the restrictions, these are just weights in dimension one, right, have the reversed property, right? We said here the converse is not true, but what can we say? Well, think of all the possible restrictions, and if you have the property for the restrictions and the constant is uniform in x naught and v, so I mean if the constant does not depend on the line that you chose, then that characterizes the property. So in a way, this property is also a one-dimensional property, right? Something that the other condition to me is not as clear. That this is more geometric. The Caffarelli-Gutierrez, I don't know how to reduce the Caffarelli-Gutierrez A infinity condition to a one-dimensional condition, right? Which is natural to expect something like that because convexity is one-dimensional. And so as a corollary, if it is strictly convex, then you get the property because if you have your strictly convex polynomial in Rn, every restriction is going to be a strictly convex polynomial in dimension one, right? And strictly convex polynomials have this property, the second derivative is going to be a strictly convex polynomial, and they have this property, and the property does not depend on the coefficients. The constant does not depend on the coefficients. So that's how you get for free, essentially, that your strictly convex polynomials will have this property, and they need not be radial again. And another way of characterizing this property, more always trying to play with the geometric flavor of this, is the following. So we have our strictly convex function phi in the nice Sobolev space. Then delta controlled by d is equivalent to this. Remember, you have this quasi-distance. So let's fix the second spot there. Let's put it in x naught, and then I have a function of the first variable, right? So I'm just measuring the distance to x naught. Then, if this thing here is 1/2 Helder continuous with respect to itself, because like this, you see, I'm putting and y there is z there, and here I have the distance between z and y, the distance, the Monge-Ampère quasi-distance, to the 1/2. That's why we say 1/2. And this is the term that this is just natural from the definition, right, of Helder continuity in metric spaces, in quasi-metric spaces. Then this smoothness of your quasi-distance that you're dealing with characterizes the geometric condition that gives you the Harnack inequality, right? And with this, notice that here there is no measure whatsoever, just the distance, right? Here there was some measure, some bit of measuring because you have the second derivative and all that, and the reverse Helder. Here there is no measure, just completely geometric way of characterizing the condition. All right. So I'll stop here. Thank you.